In this talk, we present EBF 4.2, a tool implementing black box cooperative verification approach for concurrent programs. Concurrency is prevalent in many present-day software systems. Examples of such software include computer games, ticket reservation systems, online banking, autopilots, and many others. Ensuring correctness and safety of concurrent programs is crucial, since software failures may lead to significant financial losses and affect people's well-being. Testing and verifying concurrent programs is an inherently difficult task. Different possible threads interleavings make the program execution non-deterministic. As the result, some bugs may occur only for a specific thread's order. Moreover, existing testing and verification techniques often have their various theoretical and practical limitations. A possible solution for this is cooperative verification. The main idea of cooperative verification is to implement a communication interface between different tools which allows the exchange of partial verification results for enhancing the overall verification process. In EBF, we implement an open source tool combining bounded model checking and fuzzing. The verification process in EBF consists of 4 consecutive stages: safety proving, seeds generation, falsification, and results aggregation. During safety proving stage, EBF calls the BMC engine for the given program and corresponding safety property. The BMC engine produces one of the 3 possible verdicts: safe, bug, or unknown. The safety proving stage is the only time when EBF can prove program safety. If the BMC engine returns bug, it generates a counterexample as well. A counterexample is a sequence of program inputs and a thread schedule that leads to the discovered vulnerability. All produced counterexamples are saved for further use during later stages. The seeds generation stage is a new feature that has been introduced in EBF 4.2. Here, EBF analyzes the input program by traversing its abstract syntax tree, and for each conditional branch in the program, it performs the following steps. First, it injects an error statement, such as assert 0, inside the corresponding branch. Then it runs the BMC tool on the newly instrumented program. If the BMC tool returns bug, then the counterexample that is produced with the bug verdict is converted into a seed for the fuzzer. Otherwise, if the BMC returns safe, unknown, or timeout, we move to the next branch in the program and go back to step 1. The seed generating continues until all injected errors have been detected or the stage timeout has been reached. The generated seeds greatly improve the fuzzer performance at the next stage. During the falsification stage, EBF checks whether the given program contains any vulnerabilities using fuzzing. Out-of-the-box fuzzers, such as libfuzz and AFL, are not suitable for testing concurrent programs. The main reason for this is that they cannot reliably enforce different thread schedules across different fuzzing runs. As the result, we implement an open-source gray box fuzzer called OpenGBF, and we use it as a fuzzing engine inside EBF. Its implementation is based on AFL++, and it performs some additional instrumentations to the program under test. Namely, it injects a delay function after every instruction in the program using an LLVM pass. Different delay values passed to the introduced delay functions can enforce different thread schedules. OpenGBF uses AFL++ to sample the delay values together with the program inputs, using the seeds produced at the previous stage. OpenGBF also performs some additional instrumentations, which help with generating counterexamples, ensuring atomic execution of the specified atomic blocks, and other capabilities. At the final stage, EBF performs aggregation of the results produced by the individual tools during the safety proving and the falsification stages. EBF provides two pieces of output: a verification verdict and a bug trace or counterexample if one of the tools detects a vulnerability. The decision table for the final verdict is relatively straightforward. When one of the tools returns unknown, EBF relies on the output of the other tool. However, when the BMC engine returns safe and OpenGBF outputs bug, EBF reports a conflict. This means that further analysis of the bug trace produced by OpenGBF is required. A conflict verdict can be caused by many reasons. For example, the BMC tool can be wrong about the program's safety due to over-approximations introduced by the operational models of system libraries. At the same time, OpenGBF can be wrong with respect to the given property, when the program may crash due to another vulnerability unrelated to the current property. We experimented with using different BMC tools inside EBF. We conducted our evaluation on the verification tasks from the concurrency safety main subcategory of SVComp 2022. In these experiments, we switched off witness validation within bench exec. The overall 15 minutes time limit was split between different stages of EBF in the following way. 6 minutes were allocated to the BMC engine, 5 minutes were allocated for OpenGBF, and 4 minutes were given to the results aggregation and counterexample generation. Each bench exec run was limited to 15 GB of memory. These experiments were conducted on a machine with 160 GB of RAM and 25 cores running Ubuntu 20.04. We evaluated EBF with 4 different BMC tools that achieved high positions in the concurrency category of SVComp 2022. We compared the results obtained by EBF with the results produced by each corresponding BMC tool running for the entire 15 minutes timeout. The evaluation results suggest that EBF increased the number of correctly identified vulnerabilities, while only slightly reducing the number of benchmarks that were proved safe. Here we present the results produced by EBF 4.2 in SVComp 2023. In this year competition we used ESBMC as a BMC engine inside EBF. With the newly introduced seeds generation feature, we split the overall 15 minutes timeout as follows. ESBMC was given 6 minutes during the safety proving stage, 1 minute was given for seeds generation, 5 minutes were given to OpenGBF for falsification, and the remaining 3 minutes were allocated to the results aggregation and counterexample generation. Out of 4 available subcategories within the concurrency category in SVComp 2023, EBF participated only in one of them. Here EBF scored 369 points, outperforming ESBMC that achieved 346. EBF correctly identified 15 more vulnerabilities while trading off only 4 verification tasks that it failed to prove safe. We identified several limitations of EBF and directions for future work. Firstly, the order of input variables in the counterexamples produced by the BMC tools is not always the same as the order of inputs in the program under test. This can significantly affect the quality of the generated seeds. Moreover, EBF currently provides only partial support for data race detection, and it cannot detect arithmetic overflows and memory safety violations. We are actively working on enabling support for these properties. Finally, a limitation that is characteristic of automated testing techniques in general is when a program features multiple types of bugs. During runtime, one bug can be always triggered before the other, producing false positives with respect to the given property. Thank you for your attention.